I'm going to talk to you today about rapid recovery of meteorites using weather radar. Basically, I'm going to kind of take you on a stroll through the kinds of data that this can be collected this way and how to analyze it. Can you hear me? I'm just getting weird.
I can hear you. Just tell me when to change slides. We can hear you.
Okay. The screen is just flashing red right now instead of showing slides. That's not helpful. There we go. All right. Sorry, getting moving. All right.
Just carry on.
I'm going to take you on a stroll through the kinds of data you can. Sorry?
Yeah, carry on. We can hear you.
Okay. All right. So I'm going to take you on a stroll through the kinds of data you can collect with radar and what you can tell about them, and so some statistics about falls that have occurred in the United States while the radar system has been operating. With rapid recovery, you don't collect as many meteorites as you do through other means, such as the Antarctic collection, but you collect a small number of very fresh meteorites that are useful for a range of studies. You also don't get to pick your parent body, but you also don't have to worry about your spacecraft fitting in the budget because there is none. Next slide, please. So very simple drawing of a meteorite fall, so we can start off with some terminology. Salient points I want to point out here. Your average meteoroid or asteroid hits the atmosphere going faster than 11 kilometers per second. It first becomes optically luminous around 100 kilometers altitude and remains so down to about 20 kilometers typically. Good rule of thumb there. If it's large enough and moving slow enough and material actually survives, then when it decelerates below 3 kilometers per second at about 20 kilometers, then the remaining meteorites no longer produce a plasma and they go dark, and you enter what's called dark flight. The meteorites are aerodynamically limited. They decelerate all the way to the ground, and they basically land at a spot on the ground determined by local winds. Next slide, please. Weather radars are not designed to see fireballs. They're designed to see weather. So they look very close to the ground, low elevation angles. You don't actually see the fireball itself this way. You see the falling meteorites, if any, were produced, which is nice because you get a very definitive answer on whether meteorites were produced by a particular fireball. There's one really important part of this. When the meteorites go through their dark flight, they get size sorted on the way down. Large ones move faster than small ones. So you get a kind of astrochromatography down to the ground. The 1 kilogram meteorites will reach the ground in about 90 seconds to 2 minutes. When they, next please. When the 1 kilogram, to illustrate this, when the 1 kilogram meteorites reach the ground, the 1 gram meteorites are still 12 kilometers high. So your typical meteorite fall actually produces a kind of column of fall of size sorted material on the way to the ground. And that turns out to be really useful when you detect them with meteorites or with radar, because you can calculate the mass of the meteorites seen in a given radar pixel. And I'll explain that in a bit. Next slide, please. So the U.S. NextRad radar system is 160 weather radars, WSR-88Ds shown on the right. Every yellow circle in that map in the center is basically the interaction range of one of these radars, and you can see they cover pretty much the entire United States. They operate 24 hours a day, 7 days a week, 365 days a year, and they stream data directly to the internet. You can go right on to a NOAA website and get that data as soon as it comes off the radar. It's an absolute triumph of open data. People use this stuff for studying birds, bird migrations, bat behavior, meteorite falls, all sorts of stuff that was never intended to do, but has been turned out to be very useful. Next slide, please. And what do they look like? They look like this. So the individual radar pixels don't look any different than what you get from hail or rain or snow or anything. What you the main difference here is in behavior. As I said, this is a falling column of debris. And so it tends to show up first at higher elevations as the radar is turning and propagate down to the ground They show up at the time and place where people report seeing the sky explode, and then they go away in typically about 10 minutes, plus or minus a few minutes. Here's some examples. You see that some of them are very linear. As I said, the dominant winds carry smaller meteorites downwind and produce a strewn field on the ground where you usually have the large meteorites at one end, the small meteorites at the other, and you get a linear strewn field in between. Next slide, please. What we do here at Johnson Space Center is when one of these events occurs, I will grab all the radar data showing the falling meteorites, calculate the mass, which I'll go over in a minute, and produce a strewn field by calculating where each of these each pixel worth of meteorites lands on the ground. They use a dark flight model called Jormungandr, and then extrapolate for the larger masses that don't show up well on radar and produce a strewn field map like you see in the image on the right. And we release those to the public, and then people go there and find meteorites. Next slide, please. So since the NexRad system went online about 1997, we've observed 32 separate meteorite falls with recovered meteorites, including the ones you see here. Every single meteorite you see here shows up in radar data on the way to the ground. Next slide, please. And it includes 20 unrecovered probable falls. For one reason or another, no meteorites were found. 7 of these are into water. Some of them just are too small. Nothing was recovered. We had one in Wichita, Kansas, outside of Wichita, December 2nd of this past year. And nothing's been recovered there because it fell into prairie reserve. A large part of the strewn field is prairie reserve, and there's tall grass. And that's all it takes to hide a meteorite fall. It's kind of a little frustrating, kind of amazing at how little it takes to hide a meteorite fall. But there's another 20 here that we see on radar, and we didn't recover in person. Next, please. So for 32 recovered falls, that amounts over the last 27 years of operation, that NexRad system, that amounts to a little over 1 fall per year. When you count in the 20 unrecovered ones, we're looking at just shy of 2 meteorite falls per year somewhere in the US. And that's pretty consistent. Next slide, please. This is a fall from, I want to point this one out as a fun recent one. So this happened on 10 December of last year. It's one of the largest ones we've seen in all the radar data. This is what you're looking at, in the image on the left is somebody's front door camera showing the fireball. Image on the right is a compilation of all the radar data. This one actually occurred very close to the Indianapolis radar for their airport, and it produced some stunningly detailed images of the falling meteorites. That's the purple and green pixels in this image that complement the NexRad blue and gray images. The fall was quite large. Meteorites were carried by the winds toward the northeast, and the smallest ones fell into the suburbs of Indianapolis there. Next, please. The provisional name is AMO. That's where the first meteorite was found. So it includes this is the largest meteorite found so far in this fall. You'll notice it is large. The finder had to go to a FedEx store or equivalent to get a large enough scale to put this on. Next. And this is a almost 117-pound meteorite recovered from this fall, which is about 53 kilograms. Obviously large. We're going to talk about why this is so large, or at least there's more data to be shown on this a little later in the talk. Next, please. This is another meteorite recovered from AMO. I just wanted to show this because it's a neat feature of meteorite falls. I don't think people appreciate it. This is a 9-kilogram meteorite. It hit the ground moving about 250 miles an hour. The recovery is on the right, the spot where it was recovered. That is, the meteorite is in that photo. It hasn't been dug up yet. Basically, it completely buried itself in the ground in the spot. So One takeaway here is that if the site were something different than a farmer's field, there's a potential to do quite a bit of damage. Next slide, please. So, calculating mass. I mentioned that we could calculate the mass of these meteorites. The radar can't detect meteorite masses directly. What you're looking at is basically surface area, and you can have a large number of small meteorites, a small number of large meteorites. The radar really can't tell the difference. But we know the fireball terminus altitude and time. You have to have the time to seconds accurate, which most video cameras can do nowadays. A lot of that data comes from people's front porch cameras, like I showed earlier. We know the starting point and altitude and time. We know the altitude and time to millisecond accuracy where the radar detects it. And basically, you can take the equations of motion for falling bodies and calculate the mass of the body that would go from the terminus of the fireball to where the radar pixel is. And from that, calculate the mass. And again, this is where that size sorting on the way to the ground is very, very helpful. Next slide. So let's look at some statistics, looking at all the falls since 1997. Go ahead and advance again. The blue ones here are recovered falls. The red ones are unrecovered. And we take a running average so you can see a running average. And we are basically getting better at this as time progresses. And I think the major factor here, on the right, that's the modern day. We're getting more falls as time progresses, and I think the major factor there is actually the number of people that report them. We're obviously not having any more meteorites fall. The radar data has been improved a couple of times along the way, but the major factor is the number of people who spot fireballs and report them on the internet has gone up tremendously since it started in 1997. There is a website called the American Meteor Society where people can report these seeing a fireball for free. That's probably one of the most useful sites. There's other things like the geostationary lightning mapper instruments on NOAA's latest generation of weather satellites that also detects fire.
Yeah, Mark, I think your John dropped out. We can't hear you now. Maybe Mark is gone.
Hey Mike, can you hear me?
Yes, I can hear you. I think Mark's.
I'll have Mark use my computer. How's that?
Oh yeah, sure.
Okay, honey, come on here.
Oh, and he has 5 minutes to go too once he gets there.
All right, 5 minutes. All right, can you hear me?
Yes.
All right, wonderful. Next slide, please. All right, I'll kind of skip through this quickly. So you look at the same data in terms of meteorite type, and it's pretty much a random assortment. With next, please. With the exception that the only 2 eucrites we found fell only a month apart, which is intriguing. Next slide, please. Cumulative falls by month. I was looking for any kind of pattern in the fall, see if there's any reason why you would see them more at one time a year than another. We get this data. You notice that for some reason nothing falls in May. We can all safely take our vacations there. Other than that, next, please. I looked at the same data in the meteoritical bulletin, just grab the first 150 falls and find that you get a regular, basically an average plus or minus a standard deviation. Over time, I expect that the graph on the left will turn into the graph on the right. Next question, next slide, please. Looking at it in a spatial distribution of falls. I won't go too much into this except to say that we are missing a lot of meteorite falls in the Pacific Northwest and the upper Midwest. And I think that's simply a factor of how many people see it. Also, the radars are less evenly distributed in the Pacific Northwest. They're a little farther apart, makes detection a little more difficult. Next, please. Now, so I talked about calculating mass. That's pretty straightforward. Calculating number is not as straightforward. Fundamentally, the principle is, you're getting reflectivity from a known surface area of a meteorite. If you take the total reflected power and divide by the radar cross section, you should get the number of meteorites. Next slide, please. Problem is, when I do this calculation, it's wrong by a very large margin. And that's because I am calculating it, and nobody has ever measured the radar reflectivity of fusion crust. And it is very different than the terrestrial basalt that I've used as a stand-in. There's a good and a bad to this. First of all of my measurements are relative as a result instead of quantitative. But we can get there if I can measure the reflectivity in a radar lab, which I would hope to do. The function of meteorite reflectivity versus radar size or meteorite size is shown in the upper right. And it's basically the me region reflectivity. The upside of this is that it's a complicated function, and if we can possibly use this. Basically, the complicated function ought to be slightly different for different meteorite types, especially irons, achondrites, ordinaries, and the possibility exists that I could use this data, that the sensitivity to meteorite type there, to identify the meteorite type from the radar data. This has yet to be proven, but it could be really useful, especially for the ones that we don't recover. Next slide, please. Potential is that, next, please. The potential is that basically we can identify the meteorite type before somebody actually picks one up. So once we have the mass and number, it can make a size frequency distribution. Next, please. So it looks something like this, a power law function, as you'd expect for crushing rock. Next slide, please. You measure this for a bunch of meteorite falls, you get a bunch of different answers. Next slide, please. And taking the log of each makes it a little easier to fit, a little easier to interpret. Basically, this is a log of meteorite mass versus the number of meteorites. There's two things you get from this graph. One, the higher up on the graph you are, the larger the total meteorite fall mass. And the slope of this line is a proportion of small meteorites to large meteorites. Next. Which in turn is a proxy for the mechanical strength of the originating body. This is a histogram of those slopes showing that most of them have a value of about minus 1.5. There is a subset of especially crumbly meteorites down in the -2 region. And so basically you can get a measure of the mechanical strength of a large number of meter-sized bodies as they hit the atmosphere, which should be useful to planetary defense. Next, please. And I want to point out that meteorite that I showed from last December with the exceptionally large masses in it is all the way on the right on this graph, a very flat line with a large proportion of large meteorites. This is an L5 unbrecciated shock level 0. It was basically one large homogeneous mass that came into the atmosphere and resisted breakup. Next slide, please.
Yeah, you need to finish up, Mark.
Sorry? Yes.
You need to finish up right now.
Okay. We can be done.
Go to the last slide or something.
Yeah, just keep going. This is cool, but I gotta skip it and just put up the last. That's it. Thank you.
Thank you, Mark.